an equation. In the last problem, we calculated delta G values. Given what the standard values were, you look them up or I gave them to you, you can go ahead and do that nice direct method of solving delta G. Here's another way to solve delta G too. It's an equation and it works for solving for delta G if you know this stuff. Take a look at the equation for delta G. Remember, delta G is 100% foolproof. You get a negative, spontaneous, positive, not spontaneous. Why? Because it contains enthalpy and entropy. It considers both. And by looking at both, you can make that, you can figure that out whether or not it's going to be spontaneous or not. We consider both of those other heat values. Delta S, delta T. Notice delta T has a temperature. It is temperature dependent. Okay. And we can figure out delta G. But what I want to do is not figure out delta G. What I want to do is use this equation to figure out something in the equation other than delta G. All right, let's see. What does it say? Let's look at problem number 8. Find the temperature at which the following reactions would become spontaneous. Would become spontaneous? What do you mean? Well, remember in the last video, talked about if you have delta G negative, spontaneous. Delta G positive, non-spontaneous. Well, what if delta G comes out to be 0? I mean, it could happen. It could happen, right? I mean, you put numbers in here and temperatures, and it could be 0. You can get delta G of nothing. The value comes out to be 0. What does that mean? Because it's not positive or negative. Aha, that is a great question. That is a great question, Wilma. Wilma, the answer to your question is, what does that mean if it's a 0? You have equilibrium. Okay, equilibrium. Reactions or products aren't favored. It's not favored in either direction. Equilibrium. Oh, this stuff doesn't go away. I know you want it to, but it doesn't go away. Equilibrium's coming back to haunt you, bite you. And we'll see soon that there's a G equation, a different version of this, that has a decay value right in it. So G and K related. So G, if it's a 0, means you're right at that cusp of spontaneity. A little bit this way or a little bit that way, you're either spontaneous or non-spontaneous. So 0 happens at equilibrium. We have that cusp of spontaneity. I like the word cusp. So let's take a look at this problem and use this equation to solve the change, the temperature at which something would become spontaneous. Okay, because temperature is going to make a difference here. Temperature matters. At some temperatures, certain reactions don't go in the way that you have them. Sometimes they don't do that. You have to get them to a certain temperature, or they might occur spontaneously at a particular temperature down here, but not up here. So temperature has something to do with whether or not a reaction will go spontaneously or not. Okay, let's figure this one out. Now, this time I didn't give you any equations, but I gave you information to just take it and plug into the equation and see how this works with the equation. A. Figure out what the temperature would be, what temperature would this reaction become spontaneous at, given the following values. Delta H is negative 126. So delta H, negative 126 kilojoules per mole. Now, typically when I do a lot of my problems, I don't put the units in to save some time and marker. But I'm going to, because this is going to show you something here, it's important. Minus T. We're trying to solve for the temperature here. So I'm going to put an X in for that. Okay, leave it as T if you want, or coffee, whatever you want. Delta S, given, but look at the unit. Be careful here. The unit is 84 joules. 84 joules. You can't subtract unlike units. You can't subtract kilojoules and joules. Can't do that. You can only subtract and subtract like units. So let's get that kilojoules here, or joules. One of them has to get into the other energy unit. Trust me, just get it into kilojoules. We'll get the joules for the entropy into kilojoules. And that in kilojoules is 0.084. 0.084 kilojoules per mole K. It's all right that we have a K here and we don't have one there. Either we have to have the exact same units or somebody else can have another unit and you can still subtract that. If somebody doesn't have that unit, it works. Okay, I'm leaving these units. I do want to show you one more thing as we're doing the math and what happens with the units. So we're ready to solve the problem for T. Wait a minute, you don't have a value for G, and you didn't give us one. We can't do this problem. That's two unknowns. Nope, problem, can't do it. Move on to the next one, please. No. We just talked about that. We just talked about it. What's the value for G? We're trying to figure out at the temperature which it becomes spontaneous. Becomes spontaneous means you're right on the cusp. So G at the temperature of spontaneity is 0, 0, 0. G is 0, 0, 0. Is it going to go this way? Is it going to go this way? Well, if it's 0, 0 means at the cusp of spontaneity. So 0 becomes our G value. Now we solve for X. All right, do it. I like taking this and moving it to this side of the equation. I don't like having a negative X. I'm getting rid of my negative X and bringing it over here, making it positive X. X times 0.084 kilojoules mole K equals negative 126 kilojoules per mole. Okay? Solve for X, divide both sides by 0.084. So take this, put it under here, and that's 0.084 kilojoules per mole K. So my X is by itself. Put that X here. And divide and do the math and you get the answer. All right, check it out. If you divide by something, it's the same thing as multiplying by the reciprocal. So what ends up happening, the kj and the moles cancel. They go bye. You're left with K. So the kilojoules and the moles cancel. You're left with Kelvin. And it makes sense. I mean, we're trying to find the temperature. Remember, X was my temperature. So it makes sense. But, or does it? Get an answer. Go ahead, divide. Take that, divide it by that. That's a negative. You divide a negative by a positive, you get negative. You will get a negative 1,500K. Doesn't ring a bell for you? Doesn't make you go, what? One eye up. What? Can't do it. Negative K? It's nonsensical. It doesn't make any sense. There is no such thing as negative K. So what this means is that this reaction becomes spontaneous at anything greater than negative 1,500, which doesn't exist. So what that really means, this one might be a little hard to get your head around, but here's what it means, is that this reaction becomes spontaneous at any real temperature. At any temperature. Above absolute zero, any temperature. 100 degrees? Yes. What about 20? I like it. 20 is comfortable. I like 20 degrees Celsius. Yes, at that temperature as well. This just simply means that at any temperature above this, which is a nonsensical number anyways, doesn't make any sense until you get to 0, you will have spontaneity. So at any temperature, you'll have spontaneity. Now let me just point out one more thing, and I hope this makes sense to you. This delta H was a negative. That means exothermic. That's an exothermic indication. Vast majority of the time, anything exothermic is spontaneous. Okay, keep that in mind. The delta S was a positive. We're subtracting here. That's not a negative that goes with this. It's subtracting. It's a positive number. Positive delta S's, increasing of entropy, vast majority of the time, those are spontaneous. What we've done is we've combined a very often spontaneous and a very often spontaneous number to give you a doubly absolutely spontaneous all the time number, which our delta G is, that's what it does. So this reaction should occur spontaneously at any temperature because it has a nice negative and a nice positive for our delta H and for our delta S, which both of those together give you yeah, this is going to be spontaneous, man, because both of those are very strong indicators of spontaneity on their own. Combine them, boom, spontaneous. Okay, let's try the next one. The next one, this one I'm going to make you think a little bit. You made me think on that one. Okay, we'll make you think more. All right, let's see. Here we go. On this one, we have our delta H value is negative 11.7. Negative 11.7 minus, we're trying to figure out the temperature, which it becomes spontaneous, so that's X again. S is negative 105 joules. make it kilojoules, negative 0.105. Now it's in kilojoules. I moved it over 3 times to put in kilojoules. All right, remember, at spontaneity, G is 0. Solve for x. I'm going to bring this over again. So this is x multiplied by negative 0.105 equals negative 11.7. Okay, solve for x. Divide both sides by negative 0.105. So divide both sides by negative 0.105. When you take a negative and divide it by a negative, what do you get? You get a positive. This is going to actually give me a sensible answer in terms of a number value. So if I do this out, I'll get a number value of, I think it's, 111. So it comes out to be 111. And it makes sense. It's like 11 divided by 0.1. It's like 117 divided by 105. So 111. So the spontaneity tipping temperature for this reaction is 111 degrees Kelvin. Above it or below it, then we have either spontaneous or non-spontaneous. So 111 degrees, this reaction is going, oh man, which way do I go? I don't know, which way should I go? This way? Should I go this way? Oh, should I be spontaneous or should I be non-spontaneous? Let's find out whether or not the higher temperatures make it spontaneous or whether or not the lower temperatures make it spontaneous. Let's find that out. How are we going to find that out? How? Well, now you know what T is. Let's plug in a number. So we know that T lets this equation be 0. If I take this 111 and put it in here, I will get 0. Let's see what happens if I put a number in that's greater than 111 degrees Kelvin. Maybe make it 200 degrees Kelvin. Okay, maybe 200. 200 is greater than 111. So what would happen if the temperature were 200? Let's put 200 in the equation and see what would happen. So remember, 111 is the, should it be spontaneous or not spontaneous if we change the temperature? If I make it a greater temperature than 111, I'll put 200 in here. Okay. So this is, now you gotta remember, this is not to subtract. I should redo this. Yeah, let's do this. So this is 200 times negative 0.105. 200 times negative 0.105, or this is about 10% of 200. If you do the math on that, quick math tells me 10%-ish of 200 ends up being about 20, right? Okay, if you don't believe me, go ahead and do it. Do the math out. But this is about 20. But it's a negative, and we're subtracting it. So what ends up happening is we take the negative 11.7 and add 20. Negative 11.7 and add 20. If you're $11 in the hole, you owe somebody $11, but here comes blowing in the wind a $20 bill. Well, good for you. You can pay them back, and you got money to spare. So this becomes a positive value at this temperature. This G becomes positive 8 point something. Doesn't matter what it is. It's irrelevant. The question is, what happens at temperatures above the 111 spontaneity temperature? Above 111, I just made up a number, any number is 200. Make up any number you want above 111, put it in the equation, see what happens. You will find that G comes out to be a positive value. What does that mean? Positive G, not spontaneous. So at temperatures above 111, this reaction would not be spontaneous. At colder temperatures, this reaction would be spontaneous. Let's try that. Let's try it. Let's put in a temperature below 111. 100. 100 is below 111. That's an easy one to do math too. So 100. What if I put 100 in here? Well, 100 times 0.105 is 10. 10.5. No, it'd be 10.5. So G, negative 11.7. This is minus a negative when I multiply those. So add, and that would be 10.5. Negative 11.7 plus 10.5 is negative, still negative, negative 1.2. Negative. I don't care about the number. What I care about is that. I get a negative, that's spontaneous. So temperature is below 111, spontaneous. Temperature above 111, non-spontaneous. All right, that's how we use that equation. Solving for what temperature spontaneity will happen. And remember, spontaneity, when it comes to delta G's, 0 means you're at equilibrium. Above or below that, we have the spontaneous and non-spontaneous situations. Okay?